Yeah, I mean, who wants to hear this jibber jabber again, but like right now, right? Okay, so this obviously will be cut out from this video. That's easy enough. Just chop out the first 2 minutes. But right now I'm talking to especially the 1A class. Obviously I'm talking to them on the video right now, and especially to you folks in the 1A class. You do want to watch this because this is going to be so much better than the actual class during 1A, trust me. All right, so I'm going to start with going over to demonstration land, which is that way. Oops, wrong way. Hi there. Law of conservation of momentum is the big deal of the day. And we use the law of conservation of momentum to determine what happens in collisions. So I went over this before, but here it is again. We are looking at 3 types of collisions. Now, explosions, as I mentioned before, are kind of the opposite of collision. Here's a collision. Boom. Oh, that was a collision. There's the sticky collision. The sticky collision is officially called inelastic. Then there's the bouncy collision. The bouncy collision is elastic. That's easy enough. Like elastic band, it's bouncy. Like an elastic ball, bouncy, right? Bouncy collision is elastic. Sticky, as in Velcro or glue, when they stick together, inelastic. All right, so we are initially going to be practicing the explosion type of collision in the analysis of conservation of momentum. So the anti-collision. When you have 2 objects, no matter what problem I actually give you, you can think of it as the red cart and the blue cart. Red cart is cart number 1, blue cart is 2. No matter what the objects are, you can still think of them as those. Object 1 has a mass, object 2 has a mass. Currently, they are stuck together. So they stay together until the event happens. This event is an explosion. When you have an explosion, you see object 1 going one direction. Object 2 goes in the opposite direction. You know it must go in the opposite direction because of the law of conservation of momentum. The total momentum of the system has to remain constant, has to stay the same, has to change not at all. Now, to be simple, our systems are just, in this class, are just going to be the 2 objects. The system is the red cart and the blue cart. When you define a system, you define what objects you're looking at. And by doing so, you're able to say, okay, everything that is in the system of red cart and blue cart is in the system. Everything else is outside of the system. This is important to know when we get to the actual law of conservation of momentum coming up soon. But anything inside the system cannot change the total momentum of the system. So the only forces involved here are the forces from the carts themselves as the carts push away from each other. So the carts are in the system, therefore the forces from the cart must be in the system. So when I press this trigger button, I'm just triggering. The force that I apply to trigger this really is insignificant. So this is not really. Okay. So the forces came from the springs in the carts pushing against each other. Any force within the system cannot change the momentum of the system. Okay, what is the current initial momentum of the system? What is it? When they're both here, not moving.
0 meters per second.
Yeah, well, it's just 0. And the unit of momentum is a kilogram meter per second, but the momentum is 0, which just is 0, 0. So therefore, what must be the total momentum of the system right now? When I said now, while they're moving apart. What was it before? So what must it be after? The total. 0. Must remain 0. The total momentum must remain. What is the reason that we can have 0 momentum? Yes, the red cart was moving this way. Yes, the blue cart was moving that way. The total momentum is 0 because momentum is a what quantity? Again, what kind of quantity? Begins with a V? Chat in the end.
Vector.
Yeah, okay, vector quantity.
Right.
The red has a positive momentum moving this way. Blue has a negative momentum moving that way. Okay, so once again, I've got a steel cannonball. We looked at this with Newton's third law before, and we said, okay, cannon pushes ball, so therefore reaction must be, who remembers from home? Reaction
ball pushes cannon.
Ball pushes cannon, and this explains why there is a recoil. We can use the law of conservation of momentum to determine how much that force is. Because the total momentum begins at 0. Therefore, the moment that the cannonball is fired from the cannonball must have the same momentum in one direction as the cannon has in the other direction. So if we can measure one, we can calculate the other. But quite clearly, you have to have a recoil. All right, so this is the law of conservation momentum. It states in these exact precise words, in the absence of an external force, the total momentum of a system remains unchanged. This is why it's important to define your system. I defined my system as the blue cart and the red cart. I am not included in that system of blue cart and red cart, which means if I were to push the blue and the red cart that was sitting on the table, I would exert an external force on that system. So that's why you can change the momentum of stuff, but inside the system, you can't. Here's a classic explanation. Has anybody sat in the passenger seat of the car and thought about you could push the car if you push the dashboard forward? I mean, has that even occurred to you? Yeah, it usually occurs to everybody at some point or another, and now it will. Even if you're in the back seat, see if pushing the seat in front of you causes the car to move. Well, of course it can't, because if you push forward, your back or your butt is going to be pushing backwards with an equal force in the opposite direction. You can't help that but happen. So you are in the system of the car and everything in it. You cannot change the momentum of the car because you're in the system of the car. So internal forces cannot change the momentum of the system. Oh yeah, momentum. Somebody pointed that out to me. That's a common misspelling on my part. Momentum. There we go. Everybody feels a little bit better, right? Good. Okay, red cart, blue cart. They're sitting all by themselves in their own system. If they are initially at rest, this type of problem becomes really, really simple. And most of the problems that I'll give you are for these two objects at rest when they explode apart. What we will be looking at is the simple application of the law of conservation of momentum. And for that, we have before and after. What? Before and after what? Before and after the event that happens. In this case, the event will be the explosion, the breaking up into the two parts. So before, what is the total momentum? They're just sitting there on the track, so what is the total momentum? So before, the total momentum is 0. This is white. Remember, momentum is P. Why? From the Italian. Okay. Total momentum, P with a subscript T for total, is equal to 0. So therefore, the total momentum after also has to be equal to 0. Before, the total momentum is the momentum of cart 1 plus the momentum of cart 2, which has to equal 0. Now, both P1 and P2 are 0, so we essentially have 0 plus 0 equals 0. Anybody surprised at that? That was not supposed to be difficult, and it wasn't. Okay. But after, once the explosion happens, the red cart is moving to the right. We'll just say the red cart is moving to the right, and it has a positive velocity. Blue cart is moving to the left, and the blue cart has a negative velocity. So the total momentum is found by determining, okay, what's the momentum of 1 and what's the momentum of 2? Momentum of 1, which I'm just arbitrarily determining, calling red 1 and blue 2, just because that's what it's always going to be. Red is 1, blue is 2. So the momentum, what are the two things you multiply together to determine momentum? Momentum is a combination of two things.
Force and time.
That's impulse, but it's good recollection, but that's the other thing. Momentum.
Mass and velocity.
Mass and velocity. So the momentum of cart 1 is mass of cart 1 times the velocity of cart 1. Add to that the mass of cart 2 times the velocity of cart 2. But those have to be 0. Well, how do you get one thing and add another thing and get 0? One of those things has to be, if you add 1 and something else, the second thing has to be negative. That's the point I'm getting to. So 1 plus -1 is 0. 5 plus -5 is 0. 22 plus -22 is 0. So what this is in short saying is no matter what, whatever the momentum of cart 1 is, m1v1, it has to be equal to the opposite of whatever the momentum of cart 2 is, m2v2. So let's do a sample here. And here I want to make absolutely clear, and again, I'm talking to the 1A and the 4A classes because I did not make this abundantly clear in the class. I'm posting a practice quiz to prepare you for the quiz that is coming up Thursday or Friday for you. When you type in an answer, make sure you give it in the proper variable equals quantity unit format. Not just the number, and not even just the number in the unit. Like M equals 14 kilograms. M for mass equals 14 kilograms. V equals 2.5 meters per second. Variable equal quantity unit. Every time. I'm going to stop reminding you, and you're going to get points off when it's not correctly presented. There's a reason for this. Let's start this. I'll read it out to you just in case you can't read it all. This is a simple explosion type problem with a bullet being fired from a gun. What I want you to initially do is write down the variables equal quantity unit for the known quantities plus the variable for the wanted quantity. For example, we've got two objects. The first object can be object number 1. What's mentioned first, the bullet or the gun? Bullet. The bullet's mentioned first. So ta-da, bullet is object number 1. So we want to write down mass of object 1. And what is the mass of object 1? So you write mass equal 20 grams. But even before we go on, do we use grams? No. Okay, so we want to convert this to kilograms. So go ahead and convert this to kilograms on your own and see if you do it right. Meanwhile, write out the rest of things that you know.
Kilograms.
I'll remind everybody at once. Just do what you think is right. All right, you should have this information written down. However, just a little bit more information is needed from what I've written here. Can somebody speak up? Tell me at home, what do I need to add to my known quantities and wanted quantity? Something, a couple of things, a couple little things. Somebody unmute and tell me, what's missing? Okay, it's here and here. What do I need to add?
V1 and V2.
Right. I need to very deliberately make sure that I assign the correct speed to the correct thing. So you may have to go back and look at the problem. 400 meters per second is the speed of what? The bullet or the gun? This should be pretty obvious, right? Bullet. Yeah, it's the speed of the bullet. Now, which object did I assign as object number one? I assigned object number one as the bullet. So I need to be certain that I put a subscript one. Make sure, this is seems to be pretty obvious, but a lot of people make this mistake. You need to assign the same speed to the same, you need to assign the same subscript to the same object. So bullet's number one. So the mass of the bullet should be M1. The speed of the bullet should be V1. You can do this as you read a problem. You can write it down, bullet as object one, something like that. And that makes it easy. All right, so I'm looking for V2. All right, so turning grams into kilograms. One more time. How many grams in a kilogram? Chat in the answer. How many grams in a kilogram? Right, 1,000. So everybody said 1,000. A couple went by there. I think somebody said 100. I'm not sure if you got it wrong or you just didn't tap another zero, or maybe I couldn't see it. Okay, there's 1,000. How many zeros in 1,000? I'll give you a hint. It's 3. No, that wasn't a hint. That was the answer. Okay. There's 3 zeros in 1,000. So that means you need to move the decimal 3 places. So you take the decimal point, which is right here for 20 grams, and you move it 3 places. 1, 2, 3. Notice there's an extra spot there. You have to fill it with a 0. So that means it's 0.020 kilograms. I'm going to be doing this a lot, so I'll give you grams and you have to convert to kilograms. Move the decimal 3 places. All right. This is just a 2-object simple explosion. We're trying to find the recoil speed of the gun. So we use the 2-object explosion formula, which is M1V1 equals M2V2, excuse me, negative M2V2. Next step is to rewrite this, solving for the wanted variable. We want V2. So tap in, chat in. What is the mathematical step you need to take to change this to solve for V2? In other words, V2 equals. We want to isolate V2 on one side. So that means we have to get rid of the negative M2. How do we do that? Chat it in. Some people are doing it. Algebraically, what do you do to both sides to isolate V2?
Well, first you divide -1 by both sides to stop that, and then make that other side negative M1 and V1.
Yeah.
And then you divide M2 on both sides, correct?
Yeah. So you can also do it in a single step. Just divide both sides by negative M2. That's exactly the same thing, but it looks like what you said is actually correct. But thinking of just divide both sides by negative M2, one step. So if you divide both sides by negative M2, negative M2 cancels out over here, and you get V2 is negative M1 V1 over M2. Then we do the plug and chug. We put in the numbers that we got, and we look up here. We got all the numbers right here. So negative M1 is 0.020. V1 is 400. M2 is 1. That makes an easy division, right? And so what do we get? 0.02 times 400. Chat the answer, people, after you calculate. 8, right? Negative 8 meters per second. Negative indicating it's going in the other direction. The final answer should be written in terms of the proper format that I keep asking you to, the variable equals quantity unit. So the final velocity of the gun, V2, is equal to -8 meters per second. Variable equal quantity unit. So if this were the answer, you'd have to type into the bar, variable equal quantity unit. V2 equals -8 meters per second. By the way, when you're doing subscripts, if you have to do subscripts into the bars, you don't have to worry about making them subscript. Like you'd be fine if you typed in V2 equals -8 m/s. So in your answer bar, that would be totally acceptable. Right, 8 meters per second. That's the recoil speed of the gun. By the way, 8 meters per second, is that fast? To get the idea in miles per hour, what do you do to the speed in meters per second to get the approximate equivalent in miles per hour? You multiply by 2. Just double the number. To get closer, you'd multiply by 2.2. Even closer, 2.24. But if you just double the number of meters per second, you will get the approximate miles per hour. So 8 meters per second is 16 miles per hour. It's actually closer to 18 miles per hour. Is that fast for something that you're supposed to be holding? Yeah, it is. Okay. That's why a rifle, a pistol, for example, would not have a mass of 1 kilogram. A pistol will have a mass of like 2 to 3 kilograms. This block, has anybody picked up a firearm? Have you picked up a rifle, a gun, pistol? Anybody at home? What have you always noticed about it? No matter what it is, you can always tell if it's a toy right away, just by the heft. They have to have a lot of mass. Otherwise, it's kind of funny. Every now and then, every couple of years, there's a scare that goes through the internet. This has been happening since the 90s, really. Every couple of years, they're talking about, oh, the last one was people are going to be 3D printing guns and they won't be detectable by airport security detections because they're just going to be made out of plastic. I was like, yeah, try it. Just freaking try it. If you can get a bullet to come out of a piece of plastic at 400 meters per second, that gun is going to be recoiling at almost the same speed. That makes whatever you're firing much more dangerous to the person firing this weapon than to the person on the other side. But the only way to have a high-speed bullet without a high-speed recoil is to have a massive firearm. These things are always going to be heavy. Law of conservation of momentum demands that they always be heavy. Here's the connection between Newton's third law and the law of conservation of momentum. Ultimately, they are the same law. It's actually the same law, just using different words. This actually happens a lot of times in physics when we realize this is something called a synthesis. It's not one rule over here and a different rule over there. Altogether, it's all part of the same rule. I also pointed this out in Newton's first law and Newton's second law. Really, ultimately, the same law. It just takes a lot of words and sentences to completely describe the single law of physics that's happening here. So let's start out with Newton's third law, which basically says if A exerts a force on B, then B exerts an equal and opposite force on A. So when the golf ball hits the tennis ball hits the golf ball with an equal and opposite force. The force on A has to be equal to, but opposite to, the force on B. Right? So that's Newton's third law written as a formula. The time duration of these forces must be the same, right? Try this. Try touching the table in front of you for a longer amount of time that the table touches it back. It's absurd, right? You can't. Right, okay, so in other words, contact between two objects obviously is the same time of contact. So that means if we multiply the time of contact on A, it will be the same time as the contact on B. So that means the force on A multiplied by the time of contact has to be equal to opposite the force on B multiplied by exactly the same time of contact. Now, if you remember that force times time is impulse, then what we're saying, what Newton's third law basically says is that the impulse on A has to be equal to the impulse on B, just in the opposite direction. And here we apply the impulse momentum theorem. Impulse is equal to the object's change in momentum. So this is the impulse on A. Force times time is the impulse on A. So therefore, impulse is equal to the change in momentum. So remember, P is momentum. So this says the change in momentum of A has to equal opposite the change in momentum of B. So whatever change in momentum A has, B must have the same opposite change in momentum. No matter what the change in momentum was, B must have the negative version of that. So putting in any number for the momentum change of A, you have to have the opposite momentum change of B. So therefore, the total change must be 0. So when you add them together, one of them's got to be negative, and they have to add up to 0. So if the total momentum is changed, if the total change of momentum is 0, then the total momentum before and after must stay the same. Of course, right? If the change is 0, there is no change. If there is no change, they must be the same. So this is taking us from Newton's third law to the law of conservation of momentum and realizing it's really saying the same thing. The problem, the difficulty lies in our language. Our ability to comprehend things has to be done through language. It's the only way we can think. And so very, very simple laws of nature are made much more complicated just because of the way we think. Isn't that distressing? However, mathematics simplifies things and gets you there more directly. This is why physics has math, a lot of math in it. We're only going to do the simple stuff, but it's still worth understanding why we're doing the math.